A visitor from another star system is about to make its closest approach to our sun, and what happens in that moment could confirm our greatest hopes or deepest fears. This isn't science fiction. On October 29th, an object designated 3I Atlas will hit its perihelion at a blistering 68 kilometers per second. This is the moment a single, tiny maneuver could prove it's not just a rock, but something under intelligent control. So, what is the one signal scientists are looking for? Let's explore this together. The critical moment. What if the most important astronomical event of our lifetime was hidden in plain sight? As the third confirmed interstellar object, 3I Atlas, makes its hairpin turn around the sun on October 29, 2025, it enters a region where observation becomes almost impossible. The sheer glare of our star blinds even our most powerful telescopes, creating a perfect veil for any potential activity. This is the critical moment. Traveling at over 240,000 kilometers per hour, the object is at its maximum velocity and under immense gravitational stress. According to astronomers like Dr. Karen Meach, who led the observation campaign for the first interstellar object Oumuamua, this perihelion pass is the ultimate stress test. It's where a natural comet might break apart under tidal forces, or where a manufactured craft could perform its most efficient course correction. Natural comets can also exhibit non-gravitational movement from outgassing jets, which can complicate the picture. Scientists must be able to distinguish a subtle, random outgassing event from a sustained, deliberate burn. Every piece of data gathered before it vanished into the sun's glare showed a predictable path. But the real story begins when it re-emerges. Will it follow the same path out, or will it have a new destination? The answer will define this object's place in history. GOES 19 Limitations. As 3I Atlas neared the sun, some pointed to imagery from the GOES 19 satellite as a potential way to track it through the glare. Here's the reality check. GOES 19 is a geostationary weather satellite, a masterpiece of engineering designed for one primary purpose: monitoring Earth's weather and solar flares, not faint objects from other star systems. Its instruments, the Advanced Baseline Imager and Solar Ultraviolet Imager, are optimized for tracking storms, not spotting a magnitude 12 object against the brightest thing in our sky. As science communicator Dr. Phil Plett often explains, using the wrong tool for the job gives you flawed data. The satellite's sensors lack the sensitivity and resolution, or plate scale, needed for deep space astronomy. This is like trying to read a license plate from a mile away with a pair of reading glasses. To get meaningful data, you need a meticulous process of astrometric calibration, correcting for the satellite's motion and optical distortions against a catalog of known stars. This is incredibly difficult with an instrument not built for it. While the idea is clever, it's scientifically unsound and produces results that cannot be trusted for this kind of precise work. Debunking the rumors. Why do conspiracies about alien signals spread faster than the object itself? In the lead-up to the perihelion of 3I Atlas, social media has been flooded with claims of secret engine burns and impossible course corrections, none of which stand up to scientific scrutiny. Here's what matters. The International Astronomical Union's Minor Planet Center, the global authority for these observations, has stated there is no confirmed evidence of any anomalous activity. Dr. Gareth V. Williams, the former associate director of the MPC, has spent his career emphasizing the need for rigorous, reproducible data. Most viral claims rely on visual artifacts like camera noise, cosmic rays, or hot pixels, defects on a sensor that appear as a bright spot. A widely shared video allegedly showing 3I Atlas on a GOES coronagraph was actually just a hot pixel. Dr. Michael Brown, an astronomer at Caltech known for his discoveries in the outer solar system, notes that extraordinary claims require extraordinary evidence, a standard that social media posts rarely meet. Confirming a real trajectory change isn't about drawing lines on a blurry image. It requires time-stamped raw data, precise calibration, and peer-reviewed analysis. Until the object re-emerges from the sun's glare, everything else is just speculation fueled by excitement, not evidence. The Oberth effect. What if I told you the sun's gravity well is the most powerful engine amplifier in the solar system? This isn't a theory, it's a fundamental principle of astronautics called the Oberth effect, first described by the physicist Hermann Oberth in 1927. Imagine you're pushing a child on a swing. you get the biggest result by pushing right as the swing reaches its fastest point at the bottom of its arc. The Oberth effect is the same idea, but on a cosmic scale. A spacecraft's engine provides a much greater change in energy when the craft is already moving at high speed. As 3I Atlas dives toward the sun, it accelerates, reaching its peak velocity at perihelion. Firing an engine at that precise moment maximizes the fuel's efficiency. Dr. Nikki Fox, the mission lead for NASA's Parker Solar Probe, has used this principle in reverse, using close passes to shed velocity and tighten the probe's orbit. A modest burn of just a few kilometers per second would be magnified enormously by the object's incredible speed, allowing it to radically alter its trajectory and escape velocity. For a natural comet, this is irrelevant, but for a hypothetical craft, perihelion is the single most logical and efficient moment to change its destination, saving immense amounts of propellant. Astrometry math. How do you prove an object has defied the laws of gravity? It all comes down to the cold, hard math of astrometry. This is the science of measuring the precise positions and movements of celestial bodies. It's not about taking a pretty picture. It's about plotting an object's location against the background of distant stars with incredible accuracy. Scientists use a reference map like the Gaia DR3 catalog, which has mapped over 1.8 billion stars, to create a fixed grid. Dr. Leonard Lindegren, a key architect of the Gaia mission, helped develop this system to an accuracy of micro-arcseconds. To put that in perspective, an arcsecond is 1/3600th of a degree. Gaia is thousands of times more precise than that. When observing 3I Atlas, astronomers take a series of images, each time-stamped with millisecond precision. They then calculate the object's exact position in each frame relative to the Gaia stars. By comparing this observed path to the trajectory predicted by gravitational models, they can detect any deviation. This isn't guesswork, it's a meticulous process of measurement and comparison, and it's the only way to prove a maneuver has occurred beyond any doubt. Delta V detection. What's the smallest nudge that would give away an intelligently controlled object? The key metric is called delta V, which simply means a change in velocity. For an object like 3I Atlas at perihelion, even a tiny delta V produces a huge, observable effect over time. Here's the breakdown. A burn of just 1 kilometer per second at its closest approach to the sun would cause its position in the sky to diverge by about 20 arcseconds by the time it nears Jupiter's orbit in March 2026. For context, the planet Jupiter itself is about 40 arcseconds across. A larger 7 kilometer per second burn would shift its position by several arc minutes, a gap easily detectable by mid-sized observatories. Dr. Jill Tarter, a renowned astronomer and former director of the SETI Institute, has emphasized the need for a clear, unambiguous signal that cannot be explained by natural phenomena. A sustained delta V that pulls the object outside its uncertainty envelope, the margin of error in its predicted path, would be just such a signal. If 3I Atlas does fire an engine, it will leave a clear, measurable, and undeniable signature in the sky that multiple independent observatories could confirm. Why skip Earth? If you were an interstellar traveler, why would Earth be the last place you'd want to visit? Despite what science fiction tells us, our planet is a terrible strategic target. First, there's the gravity well. Landing on Earth and taking off again requires an enormous amount of energy, a costly maneuver for any probe trying to conserve fuel. Second, there's the planetary immune system. Over 8 billion humans, a web of surveillance networks, and dedicated planetary defense protocols. As Dr. Lindley Johnson, NASA's planetary defense officer, can attest, any unexpected arrival would trigger a global and potentially hostile response. Furthermore, low Earth orbit is a cluttered and dangerous place, filled with debris that could pose a threat to an incoming craft. The object already passed Mars in early October 2025 at a distance of 28 million kilometers with no sign of deceleration. Mars, with its thin atmosphere, lower gravity, and lack of inhabitants, would have been a far more logical and safer target for reconnaissance or resource gathering. By ignoring Mars and Earth, the object's trajectory suggests a different goal, one that lies in the strategic depths of the outer solar system. The Jupiter option. If not Earth, then where? The answer may lie with the king of the solar system, Jupiter. After slingshotting around the sun, the trajectory of 3I Atlas, whether natural or altered, will carry it toward a close encounter with the gas giant. On March 16, 2026, the object is projected to pass within 54 million kilometers of Jupiter. This is the next major checkpoint. For any intelligent mission, Jupiter and its system of over 90 moons represent a perfect logistical hub. It's a treasure trove of resources, far from the complications of inter-system politics. Planetary scientists like Dr. Heidi Hammel have spent decades studying this complex system, highlighting its potential for both scientific discovery and future resource utilization. Jupiter's immense gravity could be used for another assist to reach other targets, or more importantly, to perform a braking maneuver to enter into a stable orbit around Jupiter or one of its moons. This would be a clear, unambiguous sign of intent. If a maneuver happens at the Sun, the resulting trajectory will tell us if Jupiter is the intended destination.
Ganymede resources.
What makes a moon 770 million kilometers from Earth more valuable than Earth itself? The answer is resources, without the risk. Jupiter's moon Ganymede isn't just the largest moon in the solar system, it's a world of immense strategic value. It's the only moon with its own magnetic field, providing rare protection from Jupiter's intense radiation. Its surface is covered in water ice, which can be harvested for life support and split into hydrogen and oxygen for rocket fuel. Dr. Brittany Schmidt of Cornell University researches icy worlds like Ganymede and Europa, emphasizing their potential as resource depots and even habitats. There is strong evidence that Ganymede hosts a massive subsurface ocean with more water than all of Earth's oceans combined. With gravity just 1/7 of Earth's, landing and launching from Ganymede would be incredibly efficient. Another moon, Callisto, sits outside Jupiter's main radiation belts, offering an even safer harbor. For an advanced intelligence, setting up a base by digging under kilometers of ice on a quiet, resource-rich moon is a far more logical and practical choice than dealing with the complexities of Earth.
Barnard Starlink.
Could this object be a message from our nearest stellar neighbor? One of the most intriguing, though highly speculative details about 3I Atlas is its origin point in the sky. Its approach vector traces back to the general direction of Barnard's star, a red dwarf just 6 light-years away. Discovered by astronomer Edward Emerson Barnard in 1916, Barnard's star is one of the closest stars to our Sun. Now, let's be clear, this is not proof of anything. As exoplanet expert Dr. Sarah Seeger from MIT would note, tracing an object's path back over such vast timescales is fraught with uncertainty due to the proper motion of stars. At the object's speed, the journey would have taken tens of thousands of years, and in that time, Barnard's star has moved. The alignment could be a complete coincidence. The scientific consensus puts the probability of 3I Atlas being an artifact at less than 1 in 1,000. However, it's a coincidence that is too compelling for astronomers to ignore. It keeps the question alive. As the object re-emerges from the sun's glare in late November, telescopes will be ready. The upcoming observations will replace speculation with hard data. So, here we are, standing at a rare observational threshold. On one hand, we have the predictable path of a natural interstellar comet, governed by the elegant laws of gravity. On the other, we have the tiny but world-changing possibility of a deliberate maneuver, a signature of intelligence, written in the language of orbital mechanics. The data gathered after 3I Atlas passes, the Sun will be decisive. No more rumors, no more speculation. The world's astronomers are ready to measure its path and determine its true nature. The answer is coming. What do you think is the most likely outcome? Let me know in the comments below. And don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our universe. Thanks for watching Future Facts.